Okay, so we're recording now. So here's the plan. I went and I looked at the assignments. I know I sent an email out with some of the statistics, like the average score and the number of students who've completed the assignments. And it's pretty clear that the homework 9 is the one with the lowest completion rate and the lowest averages, right? So that's going to be the focus from my end for a couple, a couple problems or so, okay? I have this problem here shown on the screen. This is the one that most people weren't getting. So we'll go over that one first. And then I have some conceptual questions here. And the point of these conceptual questions is for you to think by yourself first. And then what I'll do is I'll throw you into little groups. And what I want you to do is try and convince the other people in your group that your answer is correct. And so I'll match you up by people with different answers. I'll have you put your answers direct message to me in chat so that I can do that. And if everybody gets the right answer, then having the discussion maybe is not worth it. We can just move on to the next one. And then after that, after we cover the most missed question and a couple conceptual questions that the score was a little bit lower on, then we'll go to either student questions, or I picked out 2 examples over here on the side. We can do those ones, but I'd rather do student questions. And student questions could be from any chapter. If you guys really you're not really sure what questions, then yeah, we could do these 2 examples over here and then see where we stand. Maybe there's some more questions. So that's the plan here. So this is from homework 9, part 1. And what we'll do here is I will slowly go through this question. I looked at the answers that were submitted on mastering, and basically there's a lot of answers where you kind of remember something that you're supposed to do, but you missed something else. And then other people would answer where they remembered the other thing, but then they missed that first thing that the first student missed, something like that. So you're kind of like missing one aspect of the question on a lot of those answers. So that's what we'll do here. So I'll actually go through this question nice and slow to make sure that it makes sense here. Anybody have any questions before we start? I will read the question to you guys. So any questions before we get started? Okay, so here's the question. This is 29.8 on homework 9 part 1. The question reads, a flat circular steel loop, and I'll actually write the question here as I read it out. A flat circular steel loop of radius 75 centimeters is at rest in a uniform magnetic field as shown. The field is changing with time according to B of t, which I've already written down below. So what is B of t? Well, it's just this function right here. These are the units, capital T for Tesla. The time dependence here of the function is right here. So 1.4 times e to the minus 0.057 t. Okay, so for this question, they give us a figure, which I've kind of just copy pasted there on the left. We can see that the loop is coming out of the screen. It's kind of into or out of the screen there in that plane, that horizontal plane. And then the magnetic field is in the vertical direction, but it's making an angle 60 degrees with respect to that horizontal plane. Okay, so the amount of magnetic field that is actually penetrating that loop is not the full magnetic field, is it? So we'll have to account for that. The questions here that we're trying to answer are what is the EMF, the magnitude of the EMF. We don't care about plus or minus. We can determine the direction later, which is exactly what we'll do for part C. Question for you guys before we actually jump into the actual problem solving portion of this. What rule of thumb or law am I going to use to determine the direction of the EMF? What rule of thumb or law or equation am I going to use to determine the direction of the EMF? Direction of increasing EMF.
Faraday's law?
So Faraday's law, almost, but we kind of have another, Faraday's law is not great for figuring out the direction of something. It's great for figuring out the magnitude of the EMF. Can we think of something else that has to do specifically with the direction? Lenz's law. Lenz's law is definitely a way that we can determine the direction. But what does Lenz's law depend on? Lenz's law, yes, it is a statements, right, about determining the direction. But what comes with Lenz's law that's actually the, you know, the method that we use for finding the direction? I'm kind of surprised actually that this isn't a little bit more
Induced current?
Induced current. So how would we find the direction of the induced current? Right, it's the same question. Right hand rule. There we go. David with the correct answer here. Right hand rule. This is how we find the directions of things, right? Yes, Faraday's law. Yes, Lenz's law. But really, in practice, what do we actually do? We use the right hand rule, right? You always want to default to the right hand rule when you're trying to figure out the direction. Always, always, always default to the right hand rule. Okay, always. So, on the test, if I'm looking around, the classroom to see how you guys are doing, I should see like a lot of you are kind of with your right hands up, right? And you're kind of trying to figure out what direction these things are in, because obviously, I'm going to ask you questions about that, right? So hopefully that's clear. Now, the last thing that we'll do here, and maybe actually second to last thing, is we'll take a look at the time in which the EMF is 1/10 of its initial value. So maybe before we get started, another question for you guys. How do we determine the initial value of the EMF? What would be the strategy? So how would we determine this quantity right here? Suppose we already know part A. So we know what epsilon is. How would we figure out the initial value of the EMF? I said epsilon, but I meant the EMF. Right, exactly. So t equals 0. Just plug in t equals 0 and you have that value, right? For an exponential function like this, right, after we apply Faraday's law, what we're going to see is that the EMF is still going to be exponential, right? And so it's going to be the coefficient in front of the exponential that tells us the initial value, right? So for example, for the exponential that's here, that 1.4, that is the initial value of the magnetic field, right? Does everybody see that? So ask yourself, what value of the magnetic field would I get if I plugged in t equals 0 here, right? If I plug in t equals 0, what's that exponential going to be? Well, we have e to something times 0, right? So it's e to the 0. Any number to 0 is going to be 1. And so we can see at 1.4 Teslas there. That's the initial value of the magnetic field. Okay. Okay, so I think we've identified everything that we need to do for this problem. We've identified, we need to, we're going to need to figure out what what EMF, the initial EMF is. We're going to need to use the right-hand rule. What are we going to need to do for part A now? So you guys tell me. So now we'll go ahead and get started here on solving the problem. But what am I going to need to find the EMF? Is there a rule? Is there a law? Is there an equation? So I'm keeping a close eye on the chat here. Let me move it closer to the screen here. Faraday's law. Does everybody agree with that? Give me a thumbs up if you agree with that. Faraday's law.
I agree.
Anybody disagree with that? Can sound off in the chat. Okay, so I think we're all in agreement. We got to use Faraday's law, right? So we'll go ahead and use Faraday's law. Faraday's law says when you look at these equations, you want to repeat their meaning as you write them down. So Faraday's law says that the induced EMF is equal to minus the rate of change of the magnetic flux. Rate of change is derivative with respect to t, right? With respect to the time. It tells you that the induced EMF is proportional to the change in flux over time, right? So if the magnetic flux is changing, then you have an induced electromotive force or an induced potential difference, okay? All right, so we need to identify now this quantity magnetic flux, so phi sub m, right? Who can tell me what phi sub m is? What is the magnetic flux? How do we calculate flux? Tien says BA cosine of some angle. Good. So the magnetic flux, and in general, let's go ahead and write down the general form so that we understand, since this is kind of like a review, right? We're going to want to understand a little bit better than BA cosine theta. So in general, the flux is an integral. It's the amount of magnetic field which penetrates a small surface element, dA. And the vector dA is a vector which is normal to that surface. Okay. So in this case, on our figure over here, let's take a step back from the pink color here for a second, and let's put dA in red. And the reason I'm going to do that here is so that we can draw it over here on this figure. So what is the direction of the normal vector for this loop? The area that is horizontal, that is in that horizontal plane there with the loop. So David says straight up. Does everybody agree with that? Or does anybody think that it should be down? Who can tell me, besides Tien, David, why we wouldn't choose the normal to be down? So what would be wrong with choosing the normal vector to go down like this? Anybody have any input on that? Feel free to give your thoughts in the chat. So David has given the answer B negative question mark. What are your guys' thoughts? So why not choose DA to be pointing downward? Can you just give me a thumbs up in if you understand the question and you're thinking about the question? Just give me a thumbs up because we're kind of silent here. Okay, so you guys are thinking about it, so I can give you a little bit more time. I just don't want to I want you guys to be thinking about it. So why not choose DA pointing down? I mean, maybe, so David has given an answer. What do you guys think about David's answer? Are you referring to cosine? Okay, Kareem is messaging me. Okay, that's a valid. I mean, that's a valid concern. That's a valid concern, Kareem. That's good. Can you identify what you think is not correct about it, though? Can you try to articulate that reasoning? Does anybody else have any input on this? It certainly wouldn't be zero. There would be no cancellation. You could still do the dot product. David says he only put it straight up because it would make the smallest possible angle with B. Okay. Okay, so I'm going to talk about it now. I'm going to give just a very simple explanation. In general, flux is not a unique quantity. You're free to choose the normal vector in one of two directions. Always choose the direction which is most convenient for you. You're free to make that choice. So in this problem, choosing DA to point downward would amount to adding a negative sign into your expression. So why not choose DA to point vertically upward rather than vertically downward so that we don't incur an additional minus sign in our expression? When you take a vector and you flip it upside down, that's equivalent to multiplying it by -1, right? When you have an open surface, like we do for this loop is just a disk. It's just a ring with the middle part, that's a disk. The normal vector is pointing up or it's pointing down. There's no way to uniquely select the direction. Okay, so it could be up or down. So think about that. That is relevant for a lot of these questions. And another piece of advice, if you're not sure, oh, I don't know if I should put the vector in this direction or if I should choose it to be in this direction, just pick a direction. And then when you get to the end of your calculation, you can evaluate, okay, should I have a plus sign here or should I have a minus sign here, right? You always have the choice, but in your final answer, maybe you'll have a plus or a minus sign depending on what you chose. But oftentimes, we're after just the magnitude and we find the direction with the right-hand rule. So if I just choose the vector to be down, I'll end up with the same answer in the end anyways. What matters is everything between the answer, right? So you want to have a good strategy to approach the problem from the beginning. So it's your choice. Up or down doesn't matter. Let's choose up. It looks like it's going to be more convenient. Okay, so moving forward now. If the flux is B dot dA, then that means I can compute this dot product, giving me the magnitude of B times the magnitude of dA times the cosine of the angle between those two vectors. And in general, nothing here pulls out of the integration. So in the most general sense, you either have integral of B dot dA or you have B dA cosine theta. Then you can go about determining which quantities are constant with respect to the integration variables. So the integration variable here is dA. So for example, in this problem, the angle doesn't change with respect to dA. So that would just pull right out of the integral. Okay, so for us, we have integral of B cosine theta dA. B and cosine theta do not change with respect to the integration variable dA. B is a function of time, and a function of time is changing with time, right? But on the surface of this plane, on the surface of this loop here, which I'm trying to highlight in blue for you if you look at the figure, the magnetic field is constant everywhere on the surface. What is the value of the magnetic field on the surface? It's this value right here. It's this whole function. So if I fix a time, if I say I'm at initial time t0, and then I let some time pass, my magnetic field changes to, let's say, t final, the value of B everywhere on that surface is the same at the initial time, and it's the same at the final time. And so we would say that the magnetic field is constant on the surface. It may not be constant in time, but it's constant on the surface. It's the same everywhere on the surface. So we can pull that quantity outside of the integration. I'll try and keep the color purple here. So B cosine theta integral dA. And what is the integral of dA? Fundamental theorem of calculus. What is the integral of dA? Let's see a chat. A. Good. David is really paying attention. That's good. So the integral of dA is just A, right? If I don't have anything multiplying dA, if I have the integral of dx, right, that's just x. If I have the integral of dq, that's just q, right? If it's not changing on the surface, then it's just going to integrate to A. We have a nice level surface defined by that current loop, that steel loop. And so our answer here is just A. It seems like we're taking a really long time to just find this expression BA cosine theta, but I hope you find that the discussion that we've had along the way is valuable, right? Because this expression is not always going to be true, right? You have to understand when you can apply BA cosine theta. So I hope that you guys don't think we're wasting time here and that you actually have you see the value there of having that conversation. So in general, you need to do an integral. And there are problems, right, in the homework, maybe mostly on the challenge problems though, where you'd actually have to do an integral. So be on the lookout for that. I may end up giving you like a simple integration to do on the test. Okay. All right, so BA cosine theta is the magnetic flux. Well, if that's our magnetic flux, remember what we're looking for. We're looking for the EMF, right? We're looking for the EMF. And the EMF is the rate of change. Let's go ahead and take the magnitude. Let's go ahead and just drop the minus sign right away. Probably should have done that a little bit earlier. We're going to find the direction later. Remember, we're going to find the direction here in part C. So d by dt, I forgot my m here, d by dt of BA cosine theta which of these quantities is changing with respect to time? Somebody besides David. Which of these quantities is changing with respect to time?
Magnetic field.
Magnetic field, right? So only the magnetic field is changing with respect to time. So everything else pulls out of the integral. Excuse me, everything pulls out of the differentiation. So we have A cosine theta and then dB dt. And we should put the magnitude over dB dt here. Let's just get rid of all of the minus signs. Let's just get rid of all of the minus signs. And so you might start to think again, back to that discussion we had about choosing dA, right? Choosing the dA vector. If we're just going to take the magnitude all the time and get rid of any minus signs, then that should also indicate to you that it doesn't matter which direction you choose dA, right? It's not unique. Flux is not unique. It's not a unique quantity. But the actual physics comes from the EMF. So the EMF has to be unique. Everybody with me? Give me a thumbs up if you're ready to move forward. Okay. Let's go ahead and change colors now here for our final answer. There are some things that we need to plug in at this stage now, right? There's some things that maybe we even need to figure out first. We don't necessarily know what the area here for this loop is. We were just told the radius of the loop, 75 centimeters. So how would we calculate the area of the circular loop? What's the area of a circle?
Pi r squared.
Pi r squared, right? We better convert those centimeters to meters though, right? Better convert those centimeters to meters. So 0.75 meters. This is quite a large loop actually, 1.5 meters wide. How about the angle? What's the angle between DA and B? What's the angle between DA and B? Right, 30 degrees, right? 30 degrees. Good. So 30 degrees, we're going to need pi 0.75 squared. And E here, the EMF is going to be a function of t here. We're not plugging in a value for t, so let me go ahead and write that in. Now, what is the derivative of B of t? What is dB dt? Calculate that real quick for yourself. What is dB dt? How do we take the derivative of constant times an exponential? How do we take the derivative of the constant times exponential? Lick, did you do that derivative by hand? Good. I'll give a little bit more time so everybody has a chance for that. I know some people, whenever you get a calculus question in a non-calculus class, it always takes at least twice as long because you have to remember. So I'll give you a little bit more time here. So go through the motions of calculating that derivative. Derivative of an exponential always comes out as an exponential, right? But you have to remember the chain rule. Okay, who hasn't said anything in chat yet? So haven't heard from David Hawkins. Haven't heard from Sean. Haven't heard from Phoebe. Okay, Sean. Okay, Kareem, you agree? How about Phoebe? Okay, everybody's got the answer then. Good. All right, so when you take the derivative here, you're going to get 1.4 times that negative. I'm going to drop the negative. I'm just looking at the magnitude of this thing. Let's just drop the negative right away. Right, so 0.057 times e to the minus 0.057. Don't drop the minus sign inside the exponential, right? When there's a minus sign inside the exponential, it's still a positive function, right? And that's our answer right there with units of Tesla per second, right? The derivative with respect to t is going to divide by seconds. So we just take this thing and plug it in down here. And you guys already calculated that coefficient out in front for me, so thank you for that. So it's going to be 0.0798 e to the minus 0.057 t. Make sure you can see the decimal there. When we crunch the numbers on this thing, I kind of need to just slide on over here. When you crunch the numbers on this thing, what do we end up with? I probably need to get a calculator at this point. Go ahead, follow along with your calculator. Go ahead and calculate the coefficient there. We're going to need that coefficient because if we plug in t equals 0, the exponential is 1, right? So that coefficient is our initial EMF, which we need for part B. And then times 0.0798 e to the minus 0.057 Oh, I can just leave this part off. I just need the coefficient here. Okay, so I have an answer. So you guys let me know if you got the same answer. So we have E of t is equal to 0.1221 e to the minus 0.057 t. Units of volts. You can check for yourself that Tesla per second times meters squared is a volt. And yeah, I see you guys putting 0.122. That's fine. We can round off that one. Let me go ahead and do that as well here. Go ahead and take the eraser here. Let's get rid of that extra digit there. Move all this a little bit closer. Okay, there's our answer there for the EMF. I'm kind of in an awkward spot on the screen here, but maybe you guys in your notes can be a little bit more organized. I'm going to work vertically upwards now. So E0, by the way, this is the answer to part A right here. So maybe we should put a box around it. Yeah. So this is our answer for part A. So if I go over here to Mastering Physics and I say, okay, show me the answer. Indeed, I see that they've given the answer 0.12, not 0.122, e to the minus 0.057 t with units of volts there. Now, some of the mistakes that I see in a lot of your answers, and it might not be, exactly the same students that are here, but I see that, like for example, one person put it's technically the correct answer, but they just didn't even multiply anything out. They just plugged in a bunch of multiplications into Mastering Physics, and usually it doesn't like that. That's one of the answers there that was given. Some other answers here. This one is also a correct answer, but the student has put some like dot product multiplication symbol in their answer inside the exponential. So hopefully that person was able to catch that and get the full points. If you are one of those students, let me know. Somebody had, like, a lot of students have the wrong coefficient. They have 0.141 in front. Let's see, somebody just gives a constant, not a function of time. So that's going to be incorrect. Somebody forgot to put E. So somebody put 0.12 and then they raised that to the power of minus 0.057 t. So be careful about that, right? Always double check what you've got for your answer there. So hopefully, I mean, it looks like a lot of the students who put an incorrect answer here probably figured out what the answer was afterwards, because a lot of the thought process here looks correct, except for this one, which looks a little bit crazy, actually. I'm not sure what happened on this answer. Yeah, and this is another correct answer, but the student did not actually compute the coefficient in front of E. They just put in pi's and 0.75 squared and cosine 60. Actually, technically, the cosine 60 makes this answer incorrect. Okay, so always double check your angles there. Make sure it's the angle between the two vectors. Whenever you see that cosine theta, right, that's coming from a dot product. And the dot product tells you it's the angle between the two vectors, right? Because the dot product of two perpendicular vectors is 0, right? So in order for that to be the case, there has to be a 90-degree angle. So the cosine of 90 degrees is 0, right? Okay, so I think conceptually this question seemed to be making sense, except maybe a couple cosine 60s on some of these answers. But yeah, so does anybody have any questions, or was that kind of was that good for part A? We should go to part B now. Just give me a thumbs up if all that made sense. If it didn't, feel free to ask a question in the chat. I do see there's 7 chats I haven't addressed, so let me take a look here. Oh yeah, I know. So Tien says on Master Phys there's no pi in the final answer. I know that, yeah. If you have a pi in there, they will accept. Oh, they will accept it? Yeah, I don't know about that. Some answers here which have a pi in them are actually incorrect answers. For example, they have a cosine 60 instead of a cosine 30, something like that. So yeah, if you're plugging in the answer, usually Mastering Physics doesn't like if you like want it to kind of calculate things. And then one student says they use 60 instead of 30. I mean, it happens sometimes. Okay, let's go ahead and go to part B now, because I think everybody's ready to move on, yeah? We can just kind of slide over a little bit. We'll go ahead and change colors here for part B. Part B asks, what is the time, so we're solving for a time, when epsilon, well, I keep saying epsilon, but I really mean the EMF. It's like a script E. I don't think epsilon is the right term for that. So when the EMF is equal to 1/10 of its initial value, right? So that was why we needed to figure out what the initial value was. We can now see what the initial value was, and I actually didn't finish writing that. It's this coefficient right here. Maybe let me put it in red. This coefficient right there with units of volts is the initial EMF. Because if we were to plug in t equals 0, the exponential will become 1, right? E to the 0, and we're left with 0.122 volts. Okay, so this statement right here is essentially the same as, let's make it a slightly more precise mathematical statement. It says if I take the function e of t and I plug in some value of t, let's call it maybe t prime. Let's ask the question, what is the value of t prime here, which is some specific time. So we're not looking for the function of t, we're looking for some specific time, t prime, when this thing is equal to E0 over 10. And of course, that is going to be, oh, I accidentally wrote a 1 right here for E0. Let's fix that up. So that's 0.122. Okay, so E0 over 10 is move the decimal place over 1 spot, right? We're dividing by 10 volts, so 0.0122. And this function here will reduce to the following expression, 0.122 times e to the minus 0.057 t prime now, which is what we're going to solve for. And that's got to be equal to E0 over 10. So let's write it this way. So 1/10 0.122, which of course has this value here. But notice that we can cancel this term on both sides of the equation, right? So we're looking for that time when we're at 1/10 of the initial EMF, which is this 0.01 volts roughly. But if I write it as 1/10 of E0 in the equation, I can actually cancel E0 on both sides of the equation here. This is my E0 here. This is my E0 here, so I cancel that on both sides, leaving me with the exponential equals 1/10. So I can log both sides. Put one too many of those there. Natural log of this exponential. Feel free to work ahead at this stage. It's just algebra, right? So if you're comfortable with this, go ahead and work ahead. Oh, whoops, I forgot to put the natural log. Natural log of 10, or 1/10. When we do that, we cancel the exponentials there with the log. So E cancels with ln. On this side, we can write this as minus the natural log of 10. So 1/10 is the same as 10 to the power minus 1, right? And so when I have a power inside of a log, I bring that out as multiplication. So 10 to the minus 1 is the same as the negative logarithm of 10. I have some chats here. Let me go ahead and take a look. So people are already throwing some answers at us here. So if you're not ready for that yet, just keep working. So minus 0.057 t prime. And then we can cancel the minus signs here. So t prime is natural log of 10 divided by 0.057. And this comes out to roughly 40 seconds, 40.4 seconds to be a little bit more precise. So give me a thumbs up if you followed along there and it makes sense. Let me know if you have a question. Would you guys like me to work through it a little bit faster and maybe skip some algebra steps here and there just to kind of move a little bit quicker, or you like the pacing? I know some of you are getting the answer before I do, but maybe some others like the pace. Maybe you want it to be even slower, I don't know. Just let me know. Maybe you can direct message me if you don't want to say it in front of everyone. So now that we've finished part B, which was to go after the time there, we now want to ask about the direction, right? So how do we figure out the direction? We established we're going to have to use the right-hand rule. This loop is on a horizontal plane. If you look at the camera here, I'm using my hand here to indicate. So this is how the loop is, right? So we can use the right-hand rule in combination, obviously, with like Lenz's law and Faraday's law to determine the direction. So question for all of you. In order for this to work, we have to know if the magnetic flux is increasing or decreasing. We determined that the magnetic flux was changing only because the magnetic field is changing. So question for you guys, is the magnetic field increasing or decreasing? So you can put your answer in the chat. Is the magnetic field increasing or decreasing? So think about that. There's a couple people who haven't answered yet. Looks like Phoebe, both Davids, Lee, Kareem, Sean answered, Tian answered. So Phoebe, do you have an answer? Okay, you agree with them. Okay. All right, good. So that's the correct answer, right? Because this exponential function is decreasing with time, right? If we just take a quick little sketch just up here in the top, quick little sketch of the magnetic field, it starts out at its initial value up here, and it's going to decrease over time, right? That's what this exponential function does. It decreases because the negative inside the exponent. Okay, so if the field is decreasing, what is the direction of the change in B? Is it up or down according to this figure? What is the direction of the delta B vector? What is the direction of the delta B vector? In other words, what is the direction that the magnetic field is changing in? Can you guys hear that? Sorry. Okay, so the direction of the change vector, a couple people saying down, maybe we're a little bit unsure about that. So you have to think about final minus initial, right? If it's decreasing, is final bigger or is final smaller, right? You want to think about the final vector minus the initial vector to get the direction. We'll wait for a little bit more people to think about that and determine that direction there. You really have to visualize that, right? You can even go ahead and draw yourself another figure, right? Assume that the figure that we were given is maybe at the initial time. Draw yourself a figure for the final time and draw it to scale, right? If the magnetic field is decreasing, then what is the direction of delta B? Okay, couple people maybe haven't answered yet. Who are they? David, Sean, Tien, Duke, David, Kareem, Lick, haven't heard from you yet. Phoebe, haven't heard from you yet. Let's give an answer. Even if we're wrong, that's fine. Okay, it's a guess, that's fine. Yeah, I'll repeat the question. So, what is the direction of the delta B vector? What is the direction of the delta B vector? So you have to think about final minus initial. Which way is B changing? Right? That's what the delta B vector tells you. Right? Okay, so let's go ahead and let's talk about it now. So initially, we'll kind of scroll over here. Initially, the B vector, which I usually use green for magnetic fields, the B vector is like this. This is B initial, And if B decreases, then at some final time, sometime later, B will be like this, right? And if this is B final, so this is how you can always determine the direction of delta B. So if B is now this way, then delta B is pointing in this direction here. So if you want to be really precise about it, it's down and to the left, but I just asked you if it was up or down, and there's a really good reason for that. The loop is in the horizontal plane. So the amount that B changes parallel to the loop does not matter for Faraday's law or for Lenz's law. So if B is changing in the horizontal direction, that doesn't help us determine the direction of the induced EMF. Okay? So we've determined the direction of delta B as a vector. Now we can make a statement about Lenz's law. So Lenz's law says that induced quantities, such as the induced EMF, or the induced magnetic field, or the induced current, or the induced electric field, induced quantities always oppose the change. And the way I phrased it was they always oppose the change of the ambient quantities. Ambient meaning the values of the magnetic field, the current, the EMF, that are there before the change occurs. Okay, so we have identified the change in magnetic field. We've said it's down and to the left. Lenz's law says, okay, now you can figure out the direction of the induced quantities by looking at the negative of the change, the opposite of the change. So now we identify that this is the direction that we need to determine the induced quantities. So I'm going to put this in bold here if I can. So this is opposite the change. This is minus delta B. This is opposite the change. And that is the vector that we will use for the right-hand rule. Okay? That means once we identify the change, we can stick our thumbs in the opposite direction of the change, and that's going to help us figure everything out. Okay? So you identify delta B so that you can identify the opposite of delta B. And once you identify the opposite of delta B, you use the right-hand rule. So now I know the direction of the induced magnetic field. That's going to be up and to the right. And I know the direction of the induced current by the right-hand rule. If I stick my thumb in the upward direction, the induced current in the loop is going to be the direction my fingers are curling in. Let me see if I can get like a picture here of like a thumb with some fingers here. Okay, so this is basically what we're going to do. So this is the direction of B induced. the current is coming out at us on this side and going in on this side for the loop. I have to say, I'm pretty surprised at how well this drawing turned out. It's actually not too bad. I thought it was going to be a lot worse. So it's coming out on the left side of the loop, and it's going in on the right side of the loop. So let me see if I can draw the loop on the hand there. So what color was the loop again? It was like a yellowish, goldish color. So here is kind of like the loop, right? So the induced current is going out on the left side, in on the right side. So it must be going in this direction on that part of the loop, right? Remember, this is a circular loop. It's not a rectangular loop. So I've kind of left out the three-dimensional part of this and drawn it as a two-dimensional type of thing with the hand in the background. So it's going around in a circle according to how your fingers curl, right? So on the left side coming out, on the right side going in. That means that the induced EMF is in that direction as well. So increasing EMF is going in the same direction as the induced current. Okay, so increasing EMF induced is in the same direction as I induced. Right, that was a rule. It's a rule, but maybe we should talk a little bit about why that rule is true. Well, this loop of wire we're assuming is a wire. It has no resistance. The problem hasn't told us this is a resistive element. When you talk about conductors, you typically assume the conductor is an ideal conductor and there's no resistance to the motion of charges. And so when you apply the EMF, you induce a current in that direction, right? But in a resistive element, the potential drops across that resistive element as current flows, right? And so if we were to measure a potential difference here for this steel loop, if we attached leads to it, if we broke the loop and attached leads to it and measured the potential difference, we'd actually measure a potential difference in the opposite way as we've indicated the induced EMF. And the reason for that would be that that element would have resistance. And so when you measure the potential difference across a resistor, you would measure those voltage drops, not the induced EMF in the loop. Okay. And that was something that I did cover in that example. That was actually one of the lectures that we were being observed, where we had two magnets. So if you want to go find the video, we had like two magnets like this, and there was a loop in here, right? And we measured on some voltmeter. And so we found that, okay, the induced EMF was going to be in this direction, but then the measured potential difference was in the opposite direction. And then when you look at the meter, you can see that what's being measured is the voltage drop across a resistor, because the meter was showing negative values, but we indicated, and the meter was like plugged in like this or something. And so we indicated that the EMF on this side was higher and the EMF on this side was lower, but because this is a resistive element that we're measuring the potential difference across, then clearly we have to have a voltage drop here. And so we had the positive terminal of the, oh no, actually I've drawn it opposite here. This was the correct way. So the positive side was connected to ground, which is here, and the negative side was connected to the positive terminal of the voltage, the voltmeter, sorry. And so we actually measured a negative voltage. You can see this in the figure in the book, or if you want to go back and watch the video where we did it as an example, I kind of explained why that was the case. So you just kind of, that's something that you kind of have to remember, that if you have an induced voltage in a resistive element, of course there are going to be voltage drops across that resistive element. And so when you go to measure that, you're going to measure the voltage drop. So that's going to be opposite the induced EMF. Okay. Give me a thumbs up if we're good to move forward. Or if you have a question, feel free to ask. We can talk a little bit more about that if you want. I think maybe one of the more difficult things in this section, if you're going to apply Faraday's law, Lenz's law to find the direction, is this part right here. This is the strategy right here that you want to make sure that you study a little bit outside of doing any particular problem. Just study this bit right here. And then maybe after you study that just by itself and understand why that is the case, then go and apply that to a couple problems in the Lenz's law section to make sure that you actually are getting, you have the understanding and you can also get a correct answer there. Okay, so that it's all about identifying the change and then looking at the opposite of the change. And that comes from the minus sign in Faraday's law. And it's said, of course, that the minus sign in Faraday's law is Lenz's law. Okay, that was only like 2 thumbs up from you, so I'm assuming there's like 6 of you who still need to write things or ask questions, so please. Any questions here that we can talk about? We've completed this example problem. So we only really added like 1 more thumbs up there. So I'll call by name now. I think Lick, David, Castillo, Phoebe, Kareem, and Sean. I don't think I saw a thumbs up from any of you. So if you have a question, feel free to ask. So we can talk a little bit more about the problem. Maybe we want to review. Do we want to go through the problem real quick so we can get a kind of a complete picture, like review what we did for that? Or should we go to the next problem? So thumbs up if you want to go to the next problem. No thumbs up if you want to quickly review this problem before we move forward. So thumbs up if you want to move on. No thumbs up if you want to do a quick review of this problem. Okay, it looks like the majority wants to do a review of it. So let's go ahead and go through it real quick. So we come back over here. Let's just recap. What's the statement of the problem? The statement of the problem is, in a nutshell, we have a loop of wire and a magnetic field going through that loop. The magnetic field is changing with time. And we're asked, what is the induced electromotive force in the wire? So what is the induced EMF? The way we answer that question, we first identify if we have a changing magnetic field, then we have a changing magnetic flux. And so we can apply Faraday's law. Faraday's law tells us calculate the flux and then take the derivative of that flux with respect to time. So we go through the motions of computing the flux and then taking its derivative. And of course, if the magnetic field depends on time, then the flux will depend on time, right? So we calculated the EMF as a function of time In part B, we're asked what value of t, in other words, how many seconds will it take for this induced EMF to be 1/10 of its initial value. So we're being asked to solve for a time. So we have to be able to invert whatever function we're given, right, to solve for the variable on the inside. So that's something we can do because we have an exponential here for the time dependence, so we can take a natural log. But first we needed to identify, well, what is the actual initial EMF, right? So we found this function here at the bottom. We found this function right here for our EMF, and we identified that if we were to plug in t for the t equals 0 for the exponential, then this piece would become 1, right? E to the 0 is 1. And so this coefficient highlighted in red was our initial EMF. So once we've identified the initial EMF, we can set up our condition here that the EMF equals 1/10 of the initial EMF. Right, so that's the strategy there. So once you set that up, you just go about solving for t. So E equals 1/10 the initial value of E. So that's what we did right here. Okay. And whenever you get a problem like this, where there's an exponential involved in the expression, and you have the initial amount as a multiplying factor in front of the exponential, and you're being asked to find the value of t, which is some ratio of the initial value, you can always make this cancellation here that we have in red, the cancellation at this step. You can always make that cancellation, and that ratio 1/10 always survives, right? Because you're looking at the initial value on the left side times a function of t, and on the right side you're looking at 1/10 of the initial value, right? Or maybe you're looking at 2/5 of the initial value. And so the initial value always cancels out on both sides. Then it's just a matter of applying some algebra steps to invert the function and solve for t. In this case, we called it t prime, just to distinguish it from the function of t. So t prime is a specific time that we're looking for, and we inverted it with natural log, and then we divided one term to the other side, and we came up with 40 seconds. Okay. The last thing we were asked to do was to determine the direction, part C right here. And part C really comes from the right-hand rule plus Lenz's law. Okay? Whenever you're looking for the direction of anything, right-hand rule is what you want to go to. But you need to know what to apply the right-hand rule to, right? So there's right-hand rule, but if you don't apply it correctly, you're not going to get a valid result, right? So that's where this little explanation in the top right-hand corner comes from. So Lenz's law says that induced quantities are always opposite to the change in the ambient quantities. So if we can identify the change, then we can identify the opposite of the change, and then we can apply the right-hand rule for that opposite of change vector. Okay, so we first imagined that the magnetic field was decreasing over time, right? Because we have an exponential e to the minus t basically, so as t increases, the value of that exponential decreases over time. So that means that the magnetic field is kind of going down towards 0 over time, eventually becoming 0 for very large times. And so the change is a vector which points down and to the left, because delta is final minus initial, right? Delta is always final minus initial. So delta B is B final minus B initial. And once you've identified delta B, you know what minus delta B is. Minus delta B is the opposite of delta B, okay? So once you've identified that, then you're ready to use right-hand rule. stick your thumb in the direction of minus delta B, and that tells you everything, right? And so initially you might stick your thumb kind of up and to the right, and you're doing the right hand rule, and you're like, wait a minute. My loop is in the horizontal plane. It's not at an angle, right? That's okay, because Lenz's law and Faraday's law don't really care about changes which are parallel to the loop. So really, when you stick your thumb in the direction of minus delta B, you only need to look at the component that's perpendicular to the loop. So if you look in the camera, I have my thumb kind of at an angle, but I know the loop is like this, right? My other hand here, the loop is flat like this, horizontal. So I don't need to stick my thumb at this angle. I can stick my thumb perpendicular to the loop, right? So now my thumb is only pointing in the perpendicular direction. And then I can do right hand rule. And we did that. I drew a little picture. So the induced magnetic field is going to be in the vertical direction against the change. And the current on the left side of the loop will be coming towards us. The current on the right side of the loop will be going away from us. And the current at the point closest to us on the loop will be going from left to right. And the current in the point furthest from us into the board will be going from right to left, right? Because this thing is going around in a circle, the current. And once you've identified the direction of the induced current, the direction of the induced EMF is the same, okay? All right, so any questions? Was that, maybe you can say in chat if that was a good review, or if there was one part maybe that was a little bit unclear. 11 out of 10, okay. Okay, so a good number of you are saying it's good. Okay, so we'll go ahead. Maybe I think Lick and Phoebe, are you also good? Okay, Lick is good. Phoebe, was that good for you? Oh, your guys' names actually switched around in my Zoom interface here. Confused me for a second. Okay. All right, so let's go ahead and do a little bit of kind of individual kind of thinking about conceptual questions. And then what we'll do is after we think about the question individually, we'll come up with an answer, right? And really, I want you to focus on the reasoning, because what I'm going to do is once I read the question and I give you some time to think about and reason out an answer, I'm going to ask you to go into groups and try and convince the other person in your group that your answer is correct, right? And so I'll try to match people who have different answers in the groups. So that way there is a discussion there. There's maybe even a little bit of argumentation to try and convince the other person. And then that'll really help you guys articulate what it is that you're thinking about. It'll really help you kind of remember. It's actually a lot easier for you to remember something that you argue about, right, than maybe something that's important that you kind of, you never argued about it, right? Like think about maybe a relationship that you've had or something like that, right? Doesn't have to be with like another, like a person. It could be like parents or guardians or cousins, whatever, right? Brothers and sisters. You tend to remember that kind of, that argumentation that you have, right? So hopefully we'll try that. We'll see how that goes. So let's go ahead and read the question. Maybe rather than writing the question out by hand into your notes, you could just take a picture with your phone or something. And then that way you save some time writing it down. You can write it down in your notes afterwards. I'll go ahead and read the question now, so pay attention. A circular loop of wire lies flat on a level tabletop in a region where the magnetic field vector points straight upward. The magnetic field suddenly vanishes. As viewed from above, in what direction does the induced current flow in the loop of wire? Answer A. The direction of the induced current cannot be determined from the given information. Answer B. An induced current flows clockwise in the loop of wire. Answer C. No current is induced in the loop of wire. Answer D. An induced current flows counterclockwise in the loop of wire. So think about that for, I'll give you 2 minutes. Think about that. Really focus on the reasoning, because you're going to have to explain your reasoning to someone else. And once you come up with an answer and you're confident in your reasoning and the logic, direct message me. Don't put it in chat so everyone can see. Direct message me the letter of your answer so that I can start grouping you based on your answers. Okay, so 2 minutes starts now. If you're watching the video on YouTube, you should also be thinking about the question. Try to articulate your reasoning, maybe write it down in your notes as a way of kind of practicing, kind of thinking about these questions. Okay, another 30 seconds, and then I am going to force you to answer so that way I can match you. If we do end up with a situation where everyone has the same answer, we can just move to the next question. Okay, 15 seconds, commit to an answer. So direct message me an answer. If you're unsure, just put an answer that you feel the most strongly about, right? Okay, we still need some more people to answer. We need 2 more people to answer. Please answer. Okay, so we have pretty much almost universal agreement. Okay, there's maybe one answer which is unsure and one answer which is incorrect. So here's what we'll do. Since we have agreement amongst almost everyone, I will discuss the answer. Since I think you guys have the correct reasoning, I'll explain my reasoning and we'll go to the next one. And we'll do the discussion for the next one. If again, there's a little bit of disagreement between the answers, then I'll put you in groups. So for this question, we have a circular loop of wire which lies flat on a level tabletop. Let's draw a quick picture, and you'll find that this picture looks an awful lot like the last question that we did. The magnetic field in the loop is directly upward initially. and the magnetic field is then switched off. So now there is no magnetic field. That means that there's an induced magnetic field opposite the change. So in the last problem, I used purple to indicate the change, which means the opposite of the change is in the vertical upward direction. So this is minus delta V, and we apply right-hand rule to minus delta V. That tells us that the current will be flowing in this direction. Right? I can stick my thumb in the minus delta V direction and the current will come out at me on the left side and in on the right side. If we were to view this from above, then that means stick your thumb at your eyeball. Look at your thumb, point it towards your eyeball, and you can see that you're going around in a counterclockwise fashion. That would be answer D. Okay, so we had universal agreement there on that for the most part, so we'll go to the next question. Okay, so again, take a picture of the question maybe so you can save yourself some time on the writing, and we'll have more time overall with each other here in the review session. There is a chat here, so okay, that's fine, yeah. Okay, so we have a circular loop of wire lies flat on a level tabletop, similar to the last question. A bar magnet is held stationary above the circular loop, with its north pole pointing downward. As viewed from above, in what direction does the induced current flow in the loop of wire? So again, 2 minutes, so around 8:32, I will ask you to commit to an answer, and you can direct message me that answer. Don't say it in chat for everyone to see. Okay, 30 more seconds. Commit to an answer. Thirty more seconds, commit to an answer. Okay, and then, yeah, okay, I got a message from someone. Okay, so I believe that's everyone. Okay, again, this is a good sign. So this is a good sign. So everyone, pretty much universal agreement. Again, we had one answer that differed from the correct answer. So that's a good sign. The key here is that the magnet is held stationary above the circular loop, and it's never moved. The magnet is never moved away or moved further into the loop or out of the loop. It just stays where it is. So that means that the change is zero. There's no change in magnetic flux. There's no change in magnetic field. And that loop of wire, of course, is not changing either. It's lying flat on the tabletop. And it's asked what is the induced current? Well, that depends on Faraday's law, right? We need to have a time-changing magnetic flux in order to have a an induced current. So the answer here is B. Okay. So this indicates to me that maybe I should ask a slightly more challenging question. So I'd like to at least have one little section where we can discuss a question kind of as a group. So let me actually grab a question real quick that's maybe a little bit more challenging so we can actually have a little bit of a discussion amongst you guys. So give me 1 second here. I think I can grab one maybe from here or not there, but maybe in here. Okay. Oh, whoops, wrong chapter. This chapter. Okay, here's a question I think is, let me see if I can actually get this to show up in Paint here. This might be tricky. Always a possibility that anything that we discuss in the review section is going to show up on the test. That's always a possibility. Maybe what we'll do is we'll scale over horizontally. Let me see if I can get this to actually show up here. If I just like try to paste this. No, okay, that's not going to work. Maybe here like this. Okay, yeah, I can get this to show up, and then I can write the question out. That's no big deal. So let's go ahead and do that. So feel free to use this time to just kind of either copy the question down or, although you can still just take a picture here in a second. Okay, let me go ahead and extend this out a little bit so the answers are kind of on one line there. And then here is our figure right here. I can try and stretch this out a little bit, but it usually gets fuzzy when you do that in Paint. So let's just kind of, I guess that's pretty good, right? It's not too bad. So there's our figure for this question. This one's a little bit more challenging, so that's nice. Hopefully this is like a question where we might have a little bit of disagreement, so we can have a discussion and maybe learn a little bit more just from going through the question. Okay, so I'll read the question. Feel free to just take a picture and you can copy it into your notes later just to save yourself some time here. The long straight wire in the figure carries a current I that is decreasing with time at a constant rate. The circular loops A, B, and C all lie in a plane containing the wire. The induced EMF in each of the loops A, B, and C is such that, and then for the answers, A, no EMF is induced in any of the loops. B, a counterclockwise EMF is induced in all the loops. C, loop A has a clockwise EMF. Loop B has no induced EMF. And loop C has a counterclockwise EMF. Answer D. Loop A has a counterclockwise EMF. Loop B has no induced EMF. And loop C has a clockwise EMF. Answer E. Loop A has a counterclockwise EMF. Loops B and C have clockwise EMFs. Okay, so think about this one by yourself first. I'll give you actually, let's give a little bit more time on this one maybe. I'll give you 3 minutes on this one before you have to commit to an answer. Remember again, really try to focus on the reasoning behind your answer so that you can explain that to another person. Once you feel confident in your answer, go ahead and direct message me again, whatever answer you feel is the correct answer. And then based on how you've answered, I'll match you into groups if there's disagreement. Okay? So 3 minutes. Another minute and a half. Again, anyone watching the video on YouTube, you should be thinking about the question, coming up with an answer, maybe write down your reasoning as if you were going to explain it to someone, just to get that practice. Okay, 15 more seconds. Commit to an answer if you have not answered yet. Commit to an answer if you haven't answered. I believe there's one more person. Okay. We are pretty close to all being in agreement. However, there are a couple answers with question marks, so I'm gonna assume that means you're unsure whether or not that's the answer, but that one seems like the correct answer to you. So we will go ahead and do the discussion. I'll match you as if those of you who are unsure have have an answer which is different from somebody who might be sure of their answer. So that way there can be a little bit of discussion there if you end up with the same answer. Okay, so we'll do the breakout rooms. I'll assign the rooms manually. I think 3 rooms is enough. Okay, rooms are open. I'll give you about 4 minutes, I think a little bit more time to discuss the answer and convince each other. Okay. So go ahead and join your rooms and try and convince the other person of your answer. I will pause the recording here for this portion. Okay, so I've started up the recording again, so you've all had a chance to kind of discuss the problem in your groups. So now I'd like you to answer the question again, and this time put your answer in the chat so everyone can see the answer. So if your partner convinced you of the answer, then maybe you change your answer, or if you're sticking to your guns, you keep the same answer you had before. Oh, let me go ahead and share the question again, just so we make sure. Maybe we forgot. But there's the question. One, two, three, four, five, six, 7, 8 answers. All answers are correct. So some of you were unsure, but you had selected the correct answer. That's usually not quite good enough, right? You kind of want to know the answer and be sure. And then there was, I think, at least one other person who did not have the correct answer. So just by discussing that, like with your groups, and everybody has come to terms and understands the answer. So the way to think about this question is the same way as those other questions, right? All this material in chapter 29 hinges on kind of like 3 things: Faraday's law, Lenz's law, and like the right-hand rule, right? And maybe even later in the chapter there's like a little bit of Ampere's law corrected by Maxwell, right? But really, if you want to get to the fundamentals of this chapter, it's really Faraday's law, Lenz's law, right-hand rule, being able to use those 3 things. Okay, so hopefully you guys felt good about that. Can you give me a thumbs up if you liked that? Like little discussion there, trying to convince your partners. Nope, everybody hated it? Okay. 2 thumbs up out of 8, okay. All right, so now I'll open it up to student questions first. So the idea now, oh, actually, you know what? We've been going for almost 2 hours. We've been going for about 1 hour and 45 minutes. Let's take a break first, yeah? Who wants to take a break? Give me a thumbs up if we take like a short break, like a 10-minute break. We can always go a little bit longer than 3 hours, right? If we need to. I'm okay with that. I don't have anything else to do. I'm just out here by myself, Actually, I do have a friend over right now who's writing essays for grad school that I'm going to help later. By the way, if anybody needs help, they want me to take a look at the materials they're using for their UC applications, CSU applications, I'm willing to do that. Usually the best way to do that is in person, where you can bring your materials rather than emailing them to me and just looking at them. It's better to get some context so I can talk to you about them a little bit. So if you need that from me, I'm here for you. I've applied for many different things over the course of my career, so I tend to know what people are looking for in those applications. All right, so so we'll take a break now. So let's do like a 10-minute break. So we'll meet back here at 9:05 p.m. There was a student who joined while we were in breakout rooms. I emailed that student, so hopefully they come back. I think they joined and they just saw, oh, where is everybody? And then they just left. So hopefully they'll come back. I'm gonna go ahead and pause the recording now. Go ahead and take your break. Recording is back on. The plan now is to address student questions, which is what I would like to do, okay? So I would like it's much better if you guys ask me questions now. So between those 4 questions we already answered, that's a pretty darn good, review of chapter 29, right? The only thing we didn't really talk about was Maxwell's correction to Ampere's law. That idea of displacement current. So now it's like, you guys ask me questions so I can address your specific needs. And if nobody has any questions, which let's hope some people have some questions, we can do the 2 example problems I have on the top right of the screen there. Well, they're not example problems. They're actually problems from the back of the book.
I have a question.
Mm-hmm.
So I was doing the other day, the one of the 100 questions, and I came across this one, and I did them, and then I don't know, like it just I didn't get the right answer.
Okay.
And I couldn't figure out why. I even searched it on Google, and then their numbers are different, but I took their method. I even tried it with my numbers, and it still didn't get anything right.
Which number?
It's this one. Let's see. This one right here with the 4 very long current carrying wires in the same plane intersect 4 centimeters.
Does it tell you the number on the assignment?
Yeah.
I can't see your screen if you're trying to share screen. I can see your face though.
Oh, sorry. Hold on. Let me. Because I'm holding the book. It's problem 2824. That will be in the book.
2824. Let's see.
Yeah.
2824.
I'm not on mastering, so I don't know which number it is on mastering.
Yeah, I don't see a 2824 on there, but we can just pull the book up and take a look at it.
Yeah.
Here we are. 28, not 29. To chapter 28, and then the questions. Okay, it's 3 very long parallel wires.
No, it's the 4 very long current carrying wires in the same plane intersect to form. I'm on mastering. It should be under something that says canceling magnetic fields, like the name.
Okay, yeah, let me find it that way then. Just Control F. Canceling a magnetic field?
Yeah, that one.
Okay. Oh, 42. Okay. Four very long current carrying wires in the same plane intersect. Okay, let's go ahead and just get this question up on up here on the paint so everyone can see first. So we have an image like this. And where's my book? Here we are. Or no, I don't want the book, I want this thing. Okay. And then I'll copy the text here now. This is number 42 on test review. So number 42 on test review. I was quite surprised. One student, a couple days ago, I checked. One student had done every problem on the review assignment, and it was somebody I didn't expect to have them all done. So that's good. So hopefully that person does good on this next test, because I don't think they did that well on the first two. So hopefully that's true for everyone. So you really should get all this practice, do all these questions. You get more out of the test when you invest more time into solving problems. Okay, so four very long current carrying wires in the same plane intersect to form a square with side lengths of 46 centimeters as shown in the figure. The currents running through the wires are 8 amps, 20 amps, 10 amps, and I. Part A of this question is asking us to calculate the magnitude, so find the magnitude of the current I that will make the magnetic field at the center of the square equal to 0. Okay, that's good for part A. Now part B, what is the direction of the current? Okay, there we go. That's what we're dealing with here. So find the magnitude of the current that will make the magnetic field at the center of the square equal to 0. Oh, excuse me. Got the hiccups now. All right, what are the chats here? Okay. Just two students who need to get a room. Okay, let's take a look at how we would approach problem A. We're looking for the magnitude of the current that will make the magnetic field at the center of the square equal to 0. So that implies that we can calculate what the magnetic field is at the center using the given information. And then we can adjust the current I so that that magnetic field will be 0, right?
Mm-hmm.
So let's take a look at it here. What is the magnetic field of a current carrying wire at a distance, let's say away from the wire, a distance r?
That be mu naught I over 2 pi r.
Yes. If I asked you how to get that formula, how do you get it? What would you do?
Do the law of Biot-Savart.
Biot-Savart, that would be quite challenging.
Oh wait,
It's
no, no,
definitely
no.
possible.
Um,
Possible but challenging.
oh, Ampere's law.
Ampere's law.
Yeah.
Nice. That's exactly what you would do. So Ampere's law to get this. Right, Ampere's law is this closed loop integral equals mu naught I. So when you have dl describing a closed loop, a circle, right, then that's where your 2 pi r comes from. So the mu naught I over 2 pi r comes from Ampere's law. Okay, so if we know the side lengths of the square, that's given to us here in the problem statement. So we have a square with side length of 46 centimeters. That means we have 46, 46, 46, and 46. What is the distance from each of the wires to the midpoint here? So what is the distance, for example, from this wire to the midpoint? Anyone can answer, it doesn't have to be Duke. So if you know the answer, feel free to speak up or write it in the chat.
Wouldn't it be just half of that side line?
It'd be half of the side length, exactly. Exactly. So 23 centimeters. Do we need that information? I wonder if we need that information because I'm looking at this problem and I see, wait, this is a square, right? So all of these wires are equidistant from the center. So perhaps we don't actually need to know that. But if we're uncomfortable with proceeding through the problem without knowing that, then maybe that might be good to have that so we have an actual number. But yeah, so Sean says not in this specific case due to the symmetry, which is kind of what I'm alluding to here. So let's see how things go. We can maybe replace R with D here, and we'll say that D equals this 23 centimeters as we kind of go through this, and let's just see what happens. Okay, so now what you'd want to do is apply the principle of superposition, right? Or in other words, the superposition principle. Superposition principle. It's just a fancy way of saying add up all the vectors to get the net magnetic field. So superposition principle, right? So B net will be equal to the sum of each of those B's. So let's say B10 plus all its vectors. B, what's the other one? 8. So these are for the 10 amp current, the 8 amp current respectively. And then B20 for the 20 amp current. Oh, I'm losing control here of my mouse. There we go. And then finally, the one that we don't know, but we're going to make it whatever it needs to be. Excuse me. So that the net magnetic field is 0. Okay. Since we're going to be working with the magnitudes here of the magnetic field, we better make sure we know the direction, because these are vectors, we're going to add them like vectors, right? So if we don't have the right direction, we won't know whether we should add or subtract the magnetic fields, okay? So let's start with the leftmost wire. So everyone answer this question, okay? For the leftmost wire, the 10 amp current wire, I want you to use the right hand rule to determine whether the magnetic field is going into or out of the screen at the center point. Into or out of. You can put your answer in the chat. A lot of people giving some answers here. That's good. Need some more people though. We need some more input here. Only about half of you have answered. Two, three, four, five, seven. One person's missing here. Who's the one missing person? Okay. All right. Good. It is into, right? Right hand rule. So stick your thumb vertically, right? And your fingers are going to curl into that square in the middle. So into for the 10 amp. Now let's do the 8 amp. How about the 8 amp? So 10 amp in black. Let's do the 8 amp in orange. So for the 8 amp, again, right hand rule. Into or out of the center of that square. 8 amp current is going from left to right there in the figure. A couple people have answered. Good to see we have agreement again. Okay, let's move forward. So into is the correct answer. So I'll draw now an orange X on top of that black X there. And now for the last one here, the 20 amp current. Let's do it in this dark blue color here. What is the direction of the magnetic field at the center for this 20 amp current? Into or out of the center of the square there? Okay, we have some agreement again here. We have everybody kind of saying out of, which is correct. Good, so we put a dot here for the blue. And now, since we have 2 which are going in and 1 which is going out, it means we cannot determine the direction of the current I just yet. If all 3 of these were going into, then we would know that the current I has to go in a certain direction to cancel the others which are adding. But what did we gain by looking at the direction? We gained sign information, right? We can now add the magnitudes of these magnetic fields with a sign, either a plus sign or a minus sign. Let's take into the board to be positive. So we'll take into the board to be positive, and we'll take out of the board to be negative. I'm free to make that choice, right? So B10 is the 10 amp current. That was the one in black. That was into. Into we'll take to be positive. What is its magnitude? Well, it's mu 0 over 2 pi d. Remember, d is this 23 centimeters over here. And then a current of 10 amps. Let's just put the number 10 there, right? How about B8? Well, B8 was orange. B8 was also into the middle there. This also has a mu 0 over 2 pi d, the same distance d in the denominator, that same 23 centimeters. The magnitude of that current was 8 amps, so I'll put an 8 there. 20 was blue here, and this one was out of the screen, so we put a minus sign, mu 0 over 2 pi d. And then in parentheses, we'll put 20, the current. And then we don't quite know about BI yet, but let's go ahead and write it as a plus. And if it should have been minus, we'll end up calculating a negative value for the current, right? If we assume, let's say, I is in the direction so that the green magnetic field is coming out of the page, then we can, what did I say again? Oh yeah, yeah. So we need to assume a direction for the current I, so that B is coming out of the page. That direction by the right-hand rule would actually be vertical. You can check that for yourselves. Where's my mouse at? Here we are. So we'll assume I is in this direction. And so by the right-hand rule, the magnetic field is coming, oh, sorry, I chose the wrong direction, downward, whoops. So if it's downward, it's going into the center of the square, the magnetic field. So for the green one, that's going to be into, so we'll draw the green X there. Okay. And if we're wrong about that, if we chose I in the wrong direction, notice that the algebra that we use to solve for I will give us a negative answer if we were wrong. Okay, so we'll get a negative answer if we're wrong. If we're right, we'll get a positive answer. Okay. All right, so I see that there's a question in the chat. So Professor, you mind explaining why the 20 amp is pointing out of the page? I am not entirely sure. Yes, so if we look at the 20 amp is flowing in this direction, right? So if it's in that direction, then I take my right hand and I stick my thumb pointing to the right, and I curl my fingers around, and I see that my fingertips, so from your perspective, here, let me try to do it with respect to the camera here. So this is my right hand, and my thumb is pointing to the right. I don't know if that's how you see it, but this is my right hand, and my thumb is pointing to my right. My fingertips are coming out of the screen from my perspective. For your perspective, you put your thumb on your screen, right? And your thumb points to the right, and at the center of the square, your fingertips should be coming out at you, right? So maybe you can message me again directly and let me know if that made sense. Okay, so what's left to do is to solve the equation. Okay, it makes sense, good. So what's left to do is just simply solve. And notice, like we kind of predicted, all of the terms here have the same factor. And we have an equals 0 on the other side of our equation, which I didn't quite write just yet. Go ahead and put it in black here. So it should be equals 0. So all of these coefficients are the same. We can cancel all of them. Be careful not to to cancel the minus sign here, right? Be careful we don't cancel that minus sign. All right, so what do we have left? We have a 10. We have an 8. Now I feel like we're in kindergarten. We're adding, maybe kindergartners don't do math with these kind of numbers, but we're color coding a simple arithmetic problem at this point. Plus I, and then that's got to be equal to 0. Here we can be even more, we can have a little bit more fun here. So we'll make this black, and then we'll write it in white. How about that? So equals 0. Okay. 10 plus 8 is 18. Minus 20, negative 2, right? Add that negative 2 to the other side, and we get that I is equal to 2. Okay? I is equal to 2. Okay. Ah, Alberto, welcome. Glad you could make it. Okay, let's not forget our units here. We want to include amps. Okay. Want to include amps. That answers the first part of the question, right? So the first part of the question was to find the magnitude of this green current here in the top right. And Alberto, maybe you can just snap a quick picture of the question with your phone, maybe copy it into the notes later. So we're looking for the magnitude of that current so that the magnetic field at the center of the square is equal to 0. So we found that we could set up an equation using the superposition principle. So add up the magnetic fields vectorially. And then the coefficients were all the same. Coefficient times the current in that wire. And so we just cancel all those coefficients that are the same. Want to be careful not to cancel the minus sign there, though, on the blue term. And then it just becomes a simple arithmetic problem, basically. 10 plus 8 minus 20 is negative 2, so I is going to be positive 2 with units of amps. Okay? Excuse me. Now we need to determine the direction of the current. Well, we made a guess, and we calculated a positive value for the current. That means that we guessed correctly for the direction. So the direction indeed is in this upward direction, or no, sorry, was it down? It was the downward direction. So the current was going in the downward direction, and that's it. That is the end of the problem. Okay, so do we have any questions about that? Does that make sense?
That made more sense. Thank you. I think it was just the direction that I messed up that messed up my thinking. Thank you.
Okay. All right, so that was one student question down. So now the panel or the floor is open to you guys again. Let me know if there are any questions, if there are any particular problems you want to see from any of the homeworks or from the review. So this particular question, I would say, is maybe a question from maybe chapter 27 or chapter 28, maybe a little bit of both there. Ampere's law in particular, I believe, is chapter 28. So the floor is your guys's, so let me know what questions you'd like me to cover. Give you some time to think, maybe check your notes or something.
I have a question.
Okay, yeah.
Could you do chapter 20, like from the I think it was like a challenge problem, maybe just one part from it.
Okay, yeah, sure. Look at it.
Chapter 29, like the number was 29.68.
Okay, so probably from the part 2 is what you were saying by challenge
Yeah.
problem. Okay, so let's see what it's asking
Probably
here.
like the last part.
29.68 you said, right?
Yes.
Okay, let me read the question here. So a uniform electric field is directed axially in a cylindrical region that includes a rectangular loop of wire with total resistance R. The loop has radially oriented width A and axially oriented length B. And it sits tight against the cylinder axis as shown in the figure. The electric field is 0 at time t equals 0, and then increases in time according to eta t squared times the k hat vector. So the electric field is in the z direction. Eta is a constant with units of volts per meter times second squared. A, what is the magnitude of the displacement current through the circular loop centered on the cylinder axis with radius r less than or equal to a at time t? So part A is clear. So part A is asking about displacement current. So I can just kind of write some notes here. Let me go ahead and maybe, is it even possible to copy paste? I don't even think it's possible to copy paste.
Professor, are you on Windows?
Stuff. Yeah,
You can use Control Shift S, I think.
Control Shift S, what is that?
Sorry, Alt Shift S, and it brings up like a snippet.
Oh no, Control Shift S worked. Yeah. Okay, let's see. Yeah, let's do that. Copy, and then let's see if I can paste it. Oh, there we go. Okay. Maybe we can enlarge it a little bit. Maybe that was enlarging it too much. Thank you for that, Alberto. Okay, so here's the setup here. We've got this cylinder. It's got an electric field which is changing with respect to time, and the question wants us to calculate displacement current. I'm not going to go through the question in detail, just enough to kind of get to the part where the question is, which I'm guessing is part E, right? Or just part E. So does the current flow clockwise or counterclockwise from the perspective shown in the figure? So to find the displacement current, which is the first part through a circular loop centered on the cylinder axis at time t, displacement current is the Maxwell term in Ampere's law, mu 0 ID. So we have Ampere's law is B dot dl equals mu 0. And actually, I guess I should put the full Ampere's law first. So it's mu 0 I conduction, so the conduction current plus the displacement current. And this displacement current here we saw was equal to epsilon naught d phi e dt. That was what Maxwell postulated, right? He made a guess. He's like, it must be this because this is kind of the effect for magnetism, so it must be a similar effect. There must be symmetry there for the electric part. So it was kind of like he guessed it, and it turns out experimentally it's been shown to work very well, right? So epsilon naught times d phi e dt. So what is d phi e dt? Well, first we have to remember the electric flux is the integral of E dot dA, right? And in this problem, E depends on T, but it does not depend on the surface here. So you can see from the figure that E is constant everywhere on the surface. The vectors all have the same length, the same magnitude. And so this simplifies a little bit to E basically times A. The integral portion just becomes integral of dA. And the cosine of the angle here, if we choose dA to be in this direction, right, the angle between those two vectors is 0. So the cosine is 1, right? So just EA. And then d phi e dt then would be dE dt, and the area doesn't change with time, so multiplied by the area. So if I multiply both sides by epsilon naught, then I have the displacement current, right? So there you go for the displacement current part. Use Ampere's law to determine the magnitude of the magnetic field at a distance r less than or equal to a from the cylinder axis at time t. So we want to determine the magnitude, of the magnetic field. Well, okay, I just go straight to Ampere's law, right? So I take this answer that I get from here, and I plug it in right here, right? And notice in this little circuit here and in this loop, there's no source of voltage, right? We have no battery that's driving current flow. So when we apply Ampere's law, we have no conduction current. We just have a displacement current, right? So we can make that term zero in the expression when we do Ampere's law. Oh, so Alberto, you also had a question about this one. So that's good. So I'm glad. So we're going over it. Hopefully, just let me know if anything is not clear here, so I can slow it down. So the Ampere's law part is the integral of b dl with this term gone. So it's just equals mu 0 id, which means it equals mu 0 epsilon 0 dE dt times a. And really, probably I should put maybe partial derivative with respect to t for e there, but e only depends on t, so it's okay in this case. So once we compute the right-hand side, then obviously we can compute the left-hand side. We're going to choose a loop in the plane there for what do they call this? The ring here that's centered, the loop of wire in the middle there. Oh no, sorry. So the loop is radially oriented with A. Oh no, see, that's the rectangular one. Anyways, this loop right here is what we're talking about. This loop right here. So we're using Ampere's law to determine the magnitude of the magnetic field at distance r less than or equal to A from the cylinder axis at time t. So that means we're looking at an Amperian loop which has a radius like this inside this region here. Actually, now that I'm kind of looking at the reason I was a little bit confused there is because I think actually this loop here is our Amperian loop, because here in the picture r is less than a, right? So a is this distance. So I think I misunderstood the question initially. So this distance here is a, right? That's what they say in the figure. So this loop here is our Ampere's law loop. So dl is on this loop here. So that's dl right there. Right, so into the ordinary. So let's back up, let's clean up the drawing a little bit. So dl right here would be in this direction. Right, and going around that loop, if we view it from above, it would be going around counterclockwise. So when I go to compute Ampere's law here, dl is going to be that of a circle, right? And the magnetic field on that loop, if we have to think about it for a second, we need to rationalize, or rather reason out, if the magnetic field is going to be constant on that loop. So I look at this problem and I see the electric field is changing with time according to eta t squared k hat. So the electric field is uniform on the surface, so it's the same everywhere. So it changes everywhere on the disc of this, like in the cylinder, it changes everywhere the same amount. And so we have cylindrical symmetry. And if we have cylindrical symmetry, we can maybe think about the electric field as maybe driving a real current in a wire here. And so the cylinder is going to have a magnetic field inside, kind of similar, and maybe it's not exactly the same, but it's going to be kind of similar to what you would expect the magnetic field on the inside of a thick wire to be. And that would be increasing linearly with respect to R. So as just a kind of a heuristic approach there, so we would expect B to be proportional to R, not 1 over R, because as we increase the radius of that loop, there's more time-changing electric flux inside that loop. So as we increase the size of the loop, it has more electric field inside. So that would mean the magnetic field would be increasing as we reach the surface of the cylinder. And then once we get outside of the cylinder, that's when we would expect the magnetic field to decrease with R. So this would be like B inside. Let me know if you guys are following the logic there. So in the chat, maybe you can say, like, explain it one more time or something along those lines, or it makes sense. So B inside, I'm expecting to be proportional to R. B outside, I'm expecting to be proportional to 1 over R. Just from thinking about current flow in a wire, right? Here we have displacement current flow in a wire, right? If this cylinder is maybe a dielectric material. So I have one chat here. Can you go over it one more time? Yeah, so let's go through the reasoning one more time here. So in this problem, we have an electric field which is changing with time. That means that when we draw this cylindrical cross section here, we've defined an area and we have an electric flux through that area. If the electric field is changing with time, then that means the electric flux is changing with time. So E changes, therefore we have electric flux is changing, therefore we have quote unquote displacement current. And if we draw analogy to current flow in a long straight wire, then we would expect B to be proportional to R inside the wire and B to be proportional to 1 over R outside the wire. Did that make more sense? I think that was a more concise explanation. So let me know, did that make sense? Let me bring up Zoom. Okay, so I do see you guys using thumbs up. Can you just do it one more time? Can you give a thumbs up if that made sense? So thumbs up again if that made sense. Phoebe, are you good there? Or do you want to ask a question? Okay, Okay, let me know if you need to hear that again. So that's the idea. We do want to draw an analogy, like Alberto said. We want to draw an analogy between a situation where we have real current flow, a conduction current, and this situation where we have a displacement current. And the situation physically is pretty much the same in terms of the mathematics. In terms of the physics, it's not exactly the same, but in terms of the mathematics, it is identical. The two situations, real current versus displacement current in a vacuum. Mathematically, those are going to be the same. Okay, so now that we've established that, we know how to calculate B. It's going to be linear inside. So the magnetic field is going to increase linearly with R. All right, so that's the answer to part B, basically. Now part C. What is the magnetic flux at time t through the rectangular wire loop? Well, we know that B is proportional to R inside the cylinder, and we're definitely inside the cylinder here. I'll use pink since the cylinder is already pink. Inside this loop right here, we're inside the cylinder, so it's going to be proportional to R, the magnetic field. So if the magnetic field is proportional to R there, what is the magnetic flux? Well, the magnetic flux is integral of B dot dA. Now things are not so simple. dA will take to be dx and dy. So if we take dA to be dx and dy, and I think we can all see that the magnetic field here, since E is increasing in the vertical direction, then the opposite of that change is a right-hand rule with our fingers pointing down. We can see that the magnetic field here is coming out of this loop. You guys double check me on that. The magnetic field right here is coming out of this loop. That's B induced, which is what we're trying to calculate. Well, it's what we calculated here in this part. This part right here. We got it, what it's proportional to just by analogy. So if E increases, then we oppose that change. So B is coming out of that loop there with the resistor. Okay, so if that's the case, then that means B went from some value to a larger value. So B induced is increasing which means that if B induced increases in this loop, then there is a B induced induced. So there's a second induced magnetic field in that loop, which opposes the increase of that one there. We're not there yet, but that is a physical, real magnetic field that would be doubly induced. But let's go back to the problem at hand now. Calculating the flux. If I take dA to be in this direction here, out of the page, same as B induced, and I'll write it as a vector, we'll say it's dx dy. So this is dx, this is dy. Okay. Actually, let's change dx to dr, maybe. No, it's fine. It's fine. We can use this coordinate system here for this loop. It's not a big deal. So we have a dx and dy. I think it's a little bit more intuitive. We have a rectangle, right? We don't have a loop here. So a rectangle. So dx dy, and then it's in the z hat direction. Remember the area vector. Let's take out of the board to be the z hat direction here, right? So x cross y is positive z. So dx dy times z hat for the area vector. So if we come down here and we replace that in here, we have b dot product z hat vector times dx dy. And the magnetic field along this direction depends on x. It depends on r, but we're at a fixed value of z here for this rectangular loop. So we're going to say it depends on x. So B is going to be proportional to, so I'll now change from an equals sign to a proportionality. basically x dx dy. The dy integral is simply going to become a constant, just this constant little b right here. So proportional to the integral of x dx, which means it's going to be proportional to x squared. So I'm leaving a lot of constants out because I just want to get the general idea here, right? So you guys fill in the details in your homework. So you should have something like this, but this x squared, this should translate when you solve the problem. Maybe you can translate over that over to r squared instead of x squared if you want to, but you can also leave it as x squared because it's really the x component that's changing as you go further and further away from the center axis of the cylinder there. So here's the cylinder, right? Here's the central axis. And we're saying basically that that is the x direction there. And we have this loop right here where we have the resistor there. This is A, and this vertical here is B. Okay, any questions about that? That was kind of a long little process there. Let me know if there's any questions there on that. So we have a loop. We've got an induced magnetic field due to the time-changing electric field. So when that field is induced, we now have a flux, a magnetic flux through that current loop. So we're going to use that to calculate the time-changing magnetic flux, which I believe is the next question. So what is the magnetic flux at time t through the rectangular wire loop? So we get that by the fact that B depends on dE dt, right? So B is proportional to R, but B also depends on time from this expression right here. So that's maybe something also you need to keep in mind. You got to keep in mind that B depends on dE dt, so that's also over here. But remember that the time dependence just rides through all the integration. The time dependence, anytime you see those integrals, surface integrals like that, the time dependence just kind of scoots on through the integral. It's just kind of ignored because there's no integration over t. Okay, so now that we have that, put this over here. Now that we have that, we're ready to move to the next question, which is what magnitude of current flows in the wire? Okay, in order to find the current in the wire, you have to know the EMF. So you have to know the magnitude of the EMF is d phi m dt. So how is the magnetic flux changing, right? How is the magnetic flux changing? And then the EMF divided by the resistance is going to give the current. That's Ohm's law, right? Remember Ohm's law? You better remember it because it's likely going to show up on the exam in some form. So Ohm's law there in combination with Faraday's law. The area doesn't change, right? So since the area doesn't change, this is really going to be proportional to dB dt. Right, times the area somehow like this. Oh, actually, you know what? This it might not be so simple. It might be something more along the lines of you are going to have to do d by dt of integral of b dot dA again. So, I mean, that's something that we already calculated though. I forgot. Yeah, so we already calculated that. So there it is right there. We just take this value that we got here, this function, which somehow depends on x squared, and we're going to plug that function in. It's going to have an x squared in it. It's going to have like a time in it somewhere as well. We're going to plug that into this integral, calculate that integral. That's going to be your EMF. then apply Ohm's law, divide that EMF by the resistance to get the current. Questions about that? So that's how you find the magnitude of the current. The next is, does the current flow clockwise or counterclockwise from the perspective shown in the figure? Okay. So if we have a magnetic field induced in this loop, the current loop here, the circuit loop that we can see on the screen there, the black wires with the hot pink resistor there, the magnetic field is increasing. The induced magnetic field is increasing. So there's a doubly induced magnetic field that goes against that increase. So if you stick your thumb into the loop, because B is increasing, we go opposite of B, of the increase. So we stick our thumb into, and then our fingers wrap around in a clockwise direction. So that is going to be the direction of the induced current. So to finally answer your question here, I is going to be going in this direction, clockwise from our perspective. Let me know if that made sense, or maybe it makes no sense.
I got the answer on that one, and it said that it was counterclockwise.
Counterclockwise?
Yeah.
Okay, let me think about it again. Maybe I made a mistake here. So the electric field is increasing. So the induced magnetic field will be opposite that. So it's coming out at us in the loop. So that should be correct. And then that magnetic field is increasing. So opposite of that increase is as a doubly induced magnetic field, which goes into the page. So if we do right hand rule on that, that is clockwise. So I'm not sure. Maybe I can pull up. What was the number of this question again? 68 was it?
Yeah, 68.
Okay. Let's take a closer look here at the solution here. I can pull up the solution, see what they say here on this one. Okay, let's see. Chapter 2968. Okay, in the solutions manual, they have the following phrase: the magnetic flux through the circuit is increasing. Exactly what we said, right? This means that the induced current flows to oppose this increase. So the current is counterclockwise. So I believe they've made a mistake in the solutions. So maybe what I can do, because obviously if the magnetic flux here is increasing, right? So if E is increasing, so this is the key part here, right? So E is increasing. To oppose that change, there must be an induced electric field in the opposite direction, which means the induced electric field is downward. That means the induced magnetic field is coming out at us in that circuit loop on the right-hand side of the center of the cylinder. It's coming out. So if B induced is increasing, right? If E starts out at 0 and then E increases, then we're going to have 0 magnetic field, and then we're going to have the induced magnetic field. So the magnetic flux is increasing. Then to oppose that change, there must be a doubly induced magnetic field, which is going into that loop. And that doubly induced magnetic field will give rise to an induced voltage in the circuit loop, according to the right-hand rule. So that would indeed be clockwise, unless I'm mixing up my directions. No, that's clockwise. So there's a mistake there in the solution. So let me see if I can just give credit on this one to everyone. Okay, that should give credit to everyone on that question there. That's the 610 class. Let me make sure I do that on the 130 class as well before I forget. So does everyone understand the logic on that there? So probably a lot of you were getting that one correct, but it was telling you that you were getting it wrong. So it's definitely an involved process. There's definitely a second induced magnetic field there, which is into the page here. This is the second induced magnetic field. So B induced. Okay, Sean, what are you saying here? So B is into the screen within the current loop. So the opposed field is towards us, indicating a counterclockwise. How are you getting the direction of you're talking about the green magnetic field? Yeah, I'm pretty sure that what we have here is correct. It's an application of Lenz's law here to find the direction. Just oppose the change. It doesn't matter if it's a changing electric field or if it's a changing magnetic field. You will always oppose the change. So you always do whatever is necessary to oppose the change. Page, okay, let's take a look. So for the electric field, so an increasing electric field causes a magnetic field that curls in the direction of the right-hand rule. Well, let's see. Let me think about that for a second before I look in the book. So Ampere's law tells us how the time-changing electric field will induce where this is mu 0, epsilon 0. Oh, okay. So that does make sense. So actually the solution is correct. So I'm wrong, the solution is correct. But I'll still give you guys credit for it anyways. Here's the reason right here. This is the reason why. In Faraday's law, you have the integral of E dot dl, which is equal to the EMF. And this is equal to minus d phi m dt. And this minus sign here is crucial for application of Faraday's law. But in this case, for Ampere's law, we do not have the minus sign. We have a plus sign here. So when we have a plus sign, we're not supposed to take the opposite direction. So, okay, that was a mistake on my part. The solution is actually correct. So when we apply the right-hand rule then, if E is increasing in this direction, then that means that the magnetic field will be according to the right-hand rule. So it will actually, in fact, be going into the page on this side. So the magnetic field will be circulating around like this. So once again, I was wrong. The solution is correct. The way you determine that is by Ampere's law. You recognize here that there is no minus sign in Ampere's law like there is in Faraday's law. So when you're looking at the induced, when you're looking at a time-changing magnetic field, you always have to remember the minus sign and oppose the direction of the change. When you're looking at a time-changing electric field, you simply apply the right-hand rule in the direction of the change. Okay, so give me a thumbs up on that one if it makes sense now. Do we need to clarify that further? Maybe I can put a question like this specifically on the test. Well, it wouldn't be oh no, right? Because I've just explained how to answer the question. So ask me a question if you don't understand what I just said.
The way that I got this answer, Professor, was I treated the loop as like just like the cross-sectional area for like a wire, and then the external magnetic field that the electric field was producing was going into the circuit, and then I just went from there. I don't know. And then
That's what we did. That's what we did, right?
yeah. So I was just,
But did you have the correct direction for, so that's probably where the mistake was. Same probably mistake, right? So if you had the magnetic field coming out, that was the incorrect direction.
well, I treated the electric field as like kind of like the current, and then that was making the magnetic field point into the circuit, and then since it's increasing, then it the induced will point out of the page.
The induced magnetic field, or
Right. Yeah.
I think thinking about it in terms of the current in the loop might be a valid way of thinking about it. If you're thinking this electric field here is increasing, so that means in this circuit here, there's an increasing electric field, and so the current is flowing at an increasing rate in that direction. That might be a valid way of thinking about it.
Okay.
I'm not 100% sure. I'd have to think about that a little bit more, but it sounds correct.
Okay.
Any other questions? So again, to reiterate, this question hinges on the fact that there is no minus sign in Ampere's law. So when we go to apply the right-hand rule for the induced magnetic field due to the time-changing electric field, this part right here, sorry, this is a mistake right here. This should say phi E, so I had a mistake there. So maybe fix that if you copied that down. So that should be d phi E dt. I guess I'm making quite a number of mistakes today. Sorry about that. So when you apply Ampere's law, there's no minus sign, it's a plus sign. Okay, it's a plus sign. So the magnetic field will be induced as shown here in this picture. So if E increases, B will be in this direction. Yes, that's exactly what I think David was talking about, Sean. So you can imagine that since the electric field is increasing, that you have electric field here in this portion of the wire, perhaps, and there's a changing electric flux there in the cross section of the wire. Although the validity of that explanation maybe doesn't hold up if you have an infinitely thin wire, right? If you have an infinitely thin wire, then there's no cross-sectional area there in that wire to give you a time-changing flux. So you really do need the concept of that cylinder there. Or the Amperian loop there is fine too. Okay, so we're past 10 o'clock, but if there are any other questions, I can answer some more questions just to wrap things up. Maybe let me give you guys another conceptual question, and maybe you guys can have a little discussion if there's a little bit of disagreement. So maybe we'll do one more round of that before we call things here. So let me pull up this again. Okay, so let's maybe flip the logic here. Actually, no, I think I've tested you guys enough on that concept. Actually, let's not do that. Let's look at maybe let's look at let's take a look at this here. Okay. Something like this. Let me try that. Okay. Come here. We'll put this here. Copy this question here. Oh, it's small. Scale it up a little bit. And then we'll copy the answers here. Scale it up. Okay, so here's another question. We have a figure again. And this will be the last question, so let's make it count. So take a picture so you don't have to copy it down. You can copy it down maybe after this meeting is over. 3 particles travel through a region of space where the magnetic field is out of the page, as shown in the figure. The electric charge of each of the 3 particles is respectively A, 1 is neutral, 2 is negative, and 3 is positive. B, 1 is neutral, 2 is positive, 3 is negative. C, 1 is positive, 2 is neutral, and 3 is negative. D, 1 is positive, 2 is negative, and 3 is neutral. And then finally E, 1 is negative, 2 is neutral, and 3 is positive. Direct message me your answer in the next 1 to 2 minutes, and I will match you up in groups if there is disagreement to try and convince the other person that you're correct, that you have the correct answer. Focus on the reasoning, right? So be ready to articulate your reasoning as to why your answer is correct. It's been a while since we've looked at something like this where we're being asked to determine the direction of motion, so to speak, for these charged particles. This is chapter 27, right? Okay, commit to an answer in the next 30 seconds. Commit to an answer. Okay, 15 seconds. I still have some people who haven't answered yet. I'm going to call you out by name if you haven't answered. We have 6, 7, 8. We have one more person. Who's the missing person? Who's the missing person? Is it Kareem? No, Kareem answered. Alberto answered. Lick. David Hawken? No, David Castillo? No. Okay, Phoebe, Tien. Duke, yeah, you answered. Sean answered. Who am I missing? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, everybody. All right, perfect. There is disagreement on this question. It's like 50-50. This is good. So this is, that means you guys are going to have to really argue and really focus on the logic and the reasoning here to try and convince the other person. So let's go ahead and do new rooms here. We're going to recreate the rooms. We're going to do 2 to 3 participants per room. I'll assign them manually now. You two will go there. You two will go there. You two will go there. And then the last group will have 3 people. So you 3 will go there. Ooh, this will be interesting. Okay. So I'll come in, try not to let me distract you. I'll pause the recording so that when I join in, it's not like recording started or whatever. Try to argue and convince the other person. Of course, stay respectful, let the other person speak, take turns, so to speak. And we'll do about 5 minutes. Let's see how it goes. So opening the rooms now. So I'll pause the recording until we come back. So now everyone's back from the breakout rooms. The answer to the question is E. And I'll give a quick explanation for those of you who are watching on YouTube. So we can use the right-hand rule for the Lenz force, which tells us that the force on a moving charged particle in a magnetic field is in the direction of V cross B. So we use our right hand for that, right-hand rule. We stick our fingers in the direction of the velocity, let's say for particle 1. So kind of up and to the right. And then curl our fingers out of the page. So I have to kind of contort my arm to do that. And I see that tells me the force is down and to the right, but this particle is moving up. So it must be an electron. So I must have to reverse the direction. It must be negatively charged. So particle 1 is negatively charged. Particle 2 experiences no force. That one must be neutral because it's not experiencing the magnetic field. Particle 3, let's see, fingers in the direction of velocity, curl my fingers out of the board, and the force is kind of down and to the right. Yeah, that looks like a positively charged particle there because it's going to undergo circular motion where the force is kind of pointing down and to the right at that at that instant there near the trajectory for particle 2. Of course, we select the answer now, we can maybe eliminate some right away. So 1 is not neutral, right? Maybe if you just look at the question, you can kind of narrow it down first. We found that 1 was negative, so those 2 are gone. So E there is the correct answer. Okay. All right, so that's where we're going to end things. So I am going to stop the recording, but any students who are still here and you guys want to ask me questions, we'll go ahead and do that now.